Hi, good afternoon, everybody. Welcome back. I'm pretty sure you're well rested and finally all bimmed out from that last session with Simon and Robin. I'd like to introduce myself. My name's Peter Clark. I'm the Business Development Manager for Man and Machine for the North. And I'm going to be talking to you today around increasing profit through digital prototyping. And in around about 10 minutes, we're shortly going to be joined by Frankie, who's one of our amazing application engineers, who's going to show you some of the capabilities of prototyping and analysis throughout this. So I hope you found everything informative so far and of interest. I mean, we've gone through a lot there with mass customization and collaboration and obviously connecting kind of all the areas of the software and maximizing what you've got through there. So kind of coming into this, talking about what digital prototyping is, we always see these kind of cool images and nice cars. You know, you get some really nice, sexy Mercedes. I'm pretty sure everybody would want to own one of these. Right the way through to our, engineers for manufacturing chairs. For instance, or our good old phones, not naming that type of the phone, what's on there, no doubt, Samsung. So, with that, to get all these products to this stage, each has to go through a set of iterations because obviously it's very, very costly to build those models and those prototypes over and over to get to where you want. And this is where analysis comes in and prototyping, especially in the digital era. So as we're kind of moving on into what FEA is and finite element analysis, sounds long, sounds scientific, but please don't be afraid. This is very straightforward and a very, very clever, powerful tool for every business, every manufacturing business to have. So looking at actual digital prototyping in its essence, you can base this down to your overall product. You can base this down to the individual components within your products, whether it be springs, whether it be chains, whether it be door hinges, you name it. The idea is really looking at the longevity, the stress fracture, the pressures, the repeat use of your product, and actually looking at the lifetime of that product in its use. Prime examples. Automotive industry, I'm just taking this one as a prime point right now. You look at your suspension system and your gear arms. You kind of need to know as a manufacturer, how long is that arm going to last? How dense do I have to make it? Where's the stress and the fracture going to come for long-term usage on that vehicle as it has a live component? And manufacturing those things over and over again just to get the right formula together, it's very, very costly and hard to do so. And that's where FEA really comes into its own. So, as part of this, I'm really, really interested to kind of get your feedback on something here, I suppose, which is what you see really is going to be the average cost of using a third party for structural analysis. I'm going to give you 30 seconds. If you have a look at those costs, analyse and see what you think the actual average cost of using a third party to test your products with. So I think we're just about getting those results finally in. And yeah, we've just got them through now. So quite interesting, really, throughout this. It's quite an array of opinion, I suppose. The interesting one is, it seems to be that kind of majority of people out there are actually looking at £1,000 being the average, whether that's off actual existing knowledge of the third-party businesses that you use in there. Some of them at the top end, there may well be very, very detailed stress analysis businesses that they use, but it kind of falls in line, I suppose, with where the rest of the market really sits. It's generally around about 88% of the industry do generally pay around about £1,000 per iteration. for each individual test, which, as you can imagine, with 10 iterations of that product, that's a huge investment each time before you've even got to a point of being able to actually get that product into manufacturing. So I want to kind of keep that in mind, really, and take that into this next part, I suppose, where Frankie will take over and actually detail some of the finer points and take you through the advantages of prototyping and the analysis software within FEA. So to do that, one last thing that I wanted to kind of say is if you're still a little bit unsure about what FEA is and what prototyping is, I'm going to show you some footage now, very old footage of a test of a bridge that was done quite some time ago. But keep in mind, this is exactly why FEA is vital within any manufacturing of any structure whatsoever.
Thank you, Pete. Wow, that was a really extreme example of how products in real life can behave in unpredictable ways. My name is Francisco Perez-Smith, and I'm a mechanical engineer. And today I'd like to demonstrate to you how you can use Inventor software to predict how a product is going to behave in real life. There are many, many reasons why you'd want to make a digital prototype of your product. Mainly to see, does it work? You know, does it have efficacy? Is it perhaps as optimal as it can be? Oftentimes you'll need to limit your liability or meet insurance criteria by proving your hand calculations are correct and that the design will behave as predicted. So today, imagine that we are part of a design office and we have been given the task of verifying this design for an awning on the Autodesk building. So the design office is particularly interested to know if these brackets are up to the job. So what we're going to do is have a look at the model. Wonderful. So here we have an iLogic parametric model of the awning, and we've been asked to verify if the design works or if it doesn't work. So we've been given a very specific load case. We've been told that we have to hang 1.8 kilonewtons off the end slat here. It has to be subject to normal Earth gravity, and it's going to be fixed by pin constraints on these at the end of the beams. So how do we get started on that? The first thing that I would do in this situation is make sure that the configuration of the awning is the worst case scenario. That is to say that the awning is as long as it can be. So we'll come along to the iLogic configurator. And here I'm going to maximize its length. And I'm also going to enable a pattern on the side, which is mainly for aesthetics, but might have some structural implications. We don't know until we calculate. So here I'm going to tick on pocket pattern, click apply. And what we're going to see is that the design has become much longer, and now there is this nice pattern on the side. So let's consider what the load case would be for this scenario. What we'd have is that the bracket is held to these rectangular hollow sections via pins, and that we are hanging a 1.8 kilonewton load on the end. How is it going to behave? How do we calculate this thing? Typically, back in the day, what we'd have to do is sit down with hand calculations and try and work out, well, you know, make some assumptions there and try to work out what is the peak stress in this. But as your design becomes more and more complicated, that becomes prohibitively difficult. And this is where finite element analysis comes into it. Finite element analysis involves breaking down the problem into lots and lots of little finite elements, little bits, and then doing calculations on those bits. Today, we're going to have a look at how you can do exactly that in the Inventor environment with the Autodesk Inventor Nastran. So we'll come to Environments, Nastran. And once it loads, what we'll see is that it's already brought in a lot of the data from our design. So not only has it brought in all of the geometry of each of our components, it's also brought in the materials. So here we can see that the beams are made out of this galvanized mild steel, and the wood is made of birch. If we right click any of these materials, we can see that we get this data card, and this data card includes all your typical material properties. So here we've got mass density, and then we've got Young's modulus, Poisson's ratio. We've also got the yield strength and the tensile strength. When doing the calculations, the Nastran will use these values to tell us whether it's going to fail or succeed. So let's go ahead, and we're going to first simplify the model, because not all of these components are structural. And we can reduce the amount of computation required by reducing it to its structural elements. Here I'm going to change the model state from the master to the Nastran level of detail. And what that's going to do is it's going to get rid of all the components that aren't really subject to load in this case. Wonderful. So what we're left with are the two brackets and also the cross slats. So when describing a scenario to the solver, what we need to do is tell it how is it fixed in place, how is it constrained. So from memory and what we saw from the model, it was held in place to rectangular hollow sections via pin connections. So what we're going to do is, in Nastran, specify those pin connections now. We'll come in, zoom into the model, and here we'll come to the constraints, and we're going to specify pin constraints. So here we can say that it's free to rotate, but not free to translate. So we'll say there's our first pin connection, second pin connection, third pin connection, and fourth pin connection. Great. It was also fast to rectangular hollow sections. Now, assuming that there was preload in the bolts, there would actually be some friction between the edge of this, the side wall of this bracket and the rectangular hollow section, and that friction would actually help resist some of the loading. However, the worst case scenario is that the preloading has failed and that it's a frictionless constraint. So we'll come along here, and we're going to add in a frictionless constraint to the sides of these brackets. There's the first one. And here we have the second one. Lovely, excellent. So at the moment we have our model, and we've got material data, we've got geometric data, and we've told it how it's constrained. Next we have to tell it how it's loaded. So what forces are actually acting on this. It's sometimes easy to forget gravity. At the moment gravity is not applied to it, and it's floating in space, which is very cool but not realistic. So the first load that we're going to apply is gravity. We'll come to loads. And here we'll get a quick preview of all the different kinds of loads that we can apply. So here we've got forces, moments, hydrostatic loading, we've got pressure, we've got gravity, remote forces, many different kinds that we can use to describe the load case. So the first one that we're going to put on is gravity. We'll call it load 1, gravity. And we're going to give it the value -9810 millimeters a second squared, gravitational acceleration acting down in the Z direction. Click the little goggles to preview it. Wonderful. Gravity is acting uniformly across our structure. Next, so for the design case that we have to verify, we're going to have 1.8 kilonewtons hanging off the end slat at the end here. So to do that, we'll come along to loads. And here we're going to put the second load, so we'll say 1.8 kilonewtons load. The force is -1,800 newtons in the Z direction, acting on this face here. If we click the goggles and increase the density of the appearance, we can see that the load is being uniformly applied downwardly to the top of that slat. Lovely, excellent. So I'll just reduce the density, there we go. Beautiful. Okay, so there we've got our constraints, loads, material properties, geometric data. What do we need to do next? We need to tell it how each of these slats connect to each of the bracket arms. So ordinarily, if we wanted to get into the real nitty-gritty, we could do bolted connections in there. We could actually model in the bolts if we wanted to. We could use rigid body connectors. There's a few ways of doing this. But to keep the model simple, we're going to assume that these slats are bonded to the tops of these arms. So we're going to make sure that our default contact type here is bonded. And what Nastran is going to do is it's going to find all the surfaces that are within 0.1 millimeters of each other and glue them together, fasten them together, completely bond them together. Here we can say OK. And when we click Auto, it will go off and detect and generate all of those contacts. And we can see them here. Not that we're going to be changing them for this exercise, but if you needed different kinds of contacts, so say for example, they were allowed to come apart but not go through each other, or they were allowed to come apart but not translate across each other, or they were allowed to slide but not come apart, you can describe all of those contacts here. You can also describe things like friction and stiffness, and if you want to get into the real nitty-gritty, you can look into failure modes for welds as well. But again, we'll keep it simple for this exercise and just keep it to bonded. Lovely. So we have our contacts now. So wonderful. Let's review. We've got our material properties, geometries, constraints, loads, and we've got our contacts. So all that's really left to do is to break up the geometry into lots and lots of little bits to do the calculations on. These are called finite elements. And it's more or less an automatic process. So if we were to just leave it as it was, what we could do is click Generate Mesh. And what it's going to do is go through each part and break them down into lots and lots of little bits. By default, it breaks it down into tetrahedral elements, parabolic tetrahedral elements. So just quickly going through there. Wonderful, almost beautiful. Great. Okay, so I'm going to zoom in just to explain this a little bit better. These finite elements are what the calculations are performed on. The finer the mesh, generally speaking, the more accurate the results tend to be. So for large bits of the mesh where you're not anticipating, stresses of importance or anything like that, large elements like this are just fine. However, we are particularly interested in the peak stress in this design. Now, from your experience, you might anticipate that if you were to load this up from the wall and it were pinned by these pin joints here, you might expect that the peak stress would be around these pinned joints. So what we're going to do, quickly just hide constraints. What we're going to do is make the mesh around these pin joints a little bit finer so that when we get results for them, they'll be more accurate. Now, we could hit it with a hammer, we could come along to mesh settings here, and we could reduce the global element size, the element size for the entire mesh down. We could reduce it all to 3 millimeters, but that would make the whole mesh very, very fine, and it would take a lot of memory, and most importantly, it would take a lot of time to perform a calculation on such a fine mesh. However, Nastran gives us lots of tools that we can not only get the calculations done, but we can get them done in a timely fashion. So what I will show you now is what's called mesh control. So mesh control allows us to apply a unique mesh setting to vertices, edges, faces, and parts entirely. So I'm particularly interested in these pin joints. So what I might do is I might select these pin joints. There we go. And I might reduce the element size from 32 millimeters to 3 millimeters. Click OK. And I'll just hide those mesh controls. And now what I'm going to do is regenerate the mesh and have a look at what happens with these pin connections here. So I'll say generate mesh. Actually, I might make one last change to the settings, mesh settings. And here you can change the advanced mesh settings. So if you want to have more curved elements or project mid-side nodes, I'm going to reduce the element growth rate. This changes the rate at which small tetrahedrons turn into large tetrahedrons. So generally when you're meshing, you want nice, smooth transitions and geometry that's all captured by the tetrahedrons. So here we go. It's going ahead. It's meshing all of the slats as before. Nothing's new there. And this is the last component that will do. But when it gets to it, what you'll notice is that there's lots and lots of... It's getting there. It's getting there. There we go. So what we can see around the pin joint is that the resolution of those tetrahedrons is a lot tighter. And so we can anticipate a lot more accurate results around these pin connections. So let's go ahead and let's review. So we've got our geometry, we've got our materials, we've got our constraints, loads, we've got our contacts, we've got our mesh all sorted. I think we're good to go. Let's go ahead and run this analysis. So what it's doing is it's grabbing all of the information that we specified about the design problem, and it's converting it into a format that the machine can understand for its calculations. So say, for example, we specified a material that material has associated material properties. So say, for example, stiffness, how much it deforms with respect to an input stress. Or we might have another property, say, for example, yield strength. So all materials, particularly metals, when you apply a load to them, they'll stretch, but when you let go of the load, they'll come back together into their original shape. However, if you stress it beyond the yield strength of the material, what you'll get is plastic deformation. What that means is that the material will permanently change shape. Typically, when it comes to designs, particularly mechanical designs, but also for awnings like this, is that you want to avoid permanent plastic deformation. So what we're going to have a look at now are results, and it's going to tell us a few things. The first and generally the most interesting one is what's called the von Mises stress. The von Mises stress is the aggregate stress in any particular area of the design. So here we have, don't be freaked out by the degree by which it's deforming. That's an exaggerated plot, just to help us visualize how it's deformed. The red dotted lines, as you can see, are the undeformed edges. So let's go ahead and have a look. What we're looking at is the solid von Mises stress. So basically the aggregate stress in each of these elements. If we zoom in, we can see that, as predicted, the pin joint here has the peak von Mises stress, 235 megapascals. Now, if you happen to have remembered the material properties for this particular metal, you would remember, I remember that the yield strength for this particular metal was 207 megapascals. So basically, the stress that this thing is experiencing exceeds the yield strength of the material, which is not good, because in reality, what we see is permanent plastic deformation about that pin. Not very good. We might even see premature fatigue as well under cyclic loading. All right, so assuming that you don't know everything about all the materials, what we can do is change the plot from the von Mises stress that we see here to safety factor. So what safety factor does is it grabs the yield strength of a material and then divides it by the von Mises stress in the area. So what we get is basically a number, and that number, if it's less than 1, will mean that there will be plastic deformation. So we've got a really borderline case here, as it turns out. The yield strength of the material is just below the aggregate stress. So we can see that the minimum safety factor here is 0.9993. Not good. In reality, we would see plastic deformation, which is not good for this design. However, it may be a policy of our insurance company to say that whatever we design have to have a safety factor of at least 1.2, just to make sure that the design will survive. Even though design code just says we need a safety factor of 1 for this extreme load case, 1.2 is required for our insurance. So let's go ahead and we'll quickly, before we continue, we'll quickly see the displacement, so we can see how much this deforms under the load. And quickly load that. Okay, lovely. So what we see here, again, I mentioned that the deformation that we see here is an exaggerated plot, but we can see that the peak deformation is 20 millimeters, so not too bad at all. Hanging a very strong load off the end, we're just seeing 20 millimeters deformation over 2 meters length. So that's fine. So our design has failed. Tragic. We need to change it. We could change a number of things. If we wanted to, we might have a parameter in there that governs the thickness of the arms. If we increase the thickness of the arms, then I'm sure that we would make the arms strong enough to resist the load. However, maybe we don't have the freedom to change the geometry of the arm, but we do have the freedom to change the material. So what we're going to do is try a different material. Here we'll come along to solid 1, and we're going to change it from mild galvanized steel, and we're going to add in a new material, aluminium 6061. So common structural aluminium. Here we go. We can see off the bat the yield strength for aluminium is 275 megapascals. Looking pretty good. I've got my eye on this, the Young's modulus. And the Poisson's ratio. Let's see how it deforms under load. So what we're going to do is set it to run. Now, rather than us waiting for the calculation to go and me staring blankly at the camera, I might use this opportunity to show you some of the other calculations that are possible in Nastran. So once that starts calculating, it's producing what's called the Nastran card at the moment, which is basically the data card that Nastran reads when doing its calculations. It'll just take another second. There we go. And while that goes, we can inspect our analyses. So I breezed through it earlier, but I might just spend a little more time on it here. This is where we can define what kind of analysis we're doing. So far, what we've looked at are linear static analysis, where we've got a load acting down, nice and gently applied to the end there. But there are many, many different kinds of analysis, as you can see from this list. So here we have normal modes analysis, which tells us what are the natural frequencies of the structure. When will it resonate? We've also got buckling. So say, for example, if you've got a structure that's prone to buckling, this will tell you if it'll buckle or not. We've also got things like, pre-stress. So say, for example, you've got bolts that are preloaded. Also nonlinearities. So if you're dealing with things like plastics and polymers of all types. You've also had things like transient responses. So things like impact loading and things that are flying or moving around with great momentum. Shock response. So, if something hits the ground, how's it going to respond? And we've also got fatigue. So say, for example, you were trying to do a calculation for this, and you want to say, okay, how many times can this structure be loaded in this way? By doing a fatigue analysis, we can get a good calculation on how many cycles before the thing breaks. Very interesting to know. Okay, so I took too long on that. The calculation's done, and we've got results, so it'll just load up now. And let's see how our aluminium 6061 did in comparison to our mild steel. Okay, wonderful. So we can see our von Mises stress is 222 megapascals. Again, it's in the same area. We expect it around the pin. Very good. So let's see how it does with safety factor. Like we said, if the safety factor is greater than 1, we're okay, but we're aiming for greater than 1.2. So we'll have a look at the safety factor with regards to yield strength. And it'll load now. And wonderful, great, excellent, good. Okay, so what we can see is that the minimum safety factor, i.e. the bare minimum in the component, is 1.4. Fantastic. It means it's 1.4 times stronger than it needs to be in order to resist plastic deformation. That's good. Now, if that were our only design criteria, we'd be great. Aluminium's cheap, easy to machine, so we might be satisfied with that, but we might also care about how much does it deform. Perhaps, if it deforms too much, we might not want it. So let's have a quick look at the displacement chart. So we'll come here, click displacement, and it's going off and showing us how much it's going to displace at the end. The mild steel displaced 20 millimeters. Let's have a look at the aluminium. 52 millimeters. So way too much. It might be that 52 millimeters of deformation makes people a bit nervous when they're seeing this loaded up and it's deforming quite a bit. That might be out of spec. So we might go ahead, we can change the material again. And this time, rather than aluminium, let's go ahead and choose a high strength, low alloy steel. So we'll come to select material, steel, high strength, low alloy. By the way, Autodesk comes with many materials in their library, but you can also import and define your own. This doesn't have to be just metals. It can be polymers or ceramics or even laminates like carbon fiber. Interesting stuff. So there we go. We see approximately the same yield strength, but it should be a bit stiffer. And rather than go through all the arduous calculations again, I'm just going to load results that I prepared earlier. So here I'll say load results and find the folder that contains this calculations. And here I've saved some results that I've pre-calculated. So linear static stress, high strength steel. And so we can save 2 minutes of calculation by cheating now. All right. And what we should see momentarily, if we actually click it, are the results. There we go. Lovely. So, nope, not the results I was expecting. Let's go ahead and run it again just in case. So what we're expecting is a slightly different behavior from this material. So the material's yield strength is much the same as aluminium, so I anticipate that it's going to survive. It's going to be heavier, so gravity is going to take more of a toll on it, so maybe that will increase the stress. How do we know? We could do the hand calculations. We might be there for 3/4 of a day, or we could just plug it into Nastran and have a quick look. The other thing that I'm anticipating is that this steel is quite a bit stiffer than aluminium, so while I expect that it will pass the stress test, I want to see how much it deforms at the end. So it shouldn't take too long. Now, the advantage of doing it in this way, and I guess I've breezed over the point, is that you can take an iterative approach to your design. So if you had, say, for example, a parameter that governed the thickness of each of these brackets, you could, say, start off with a very, very thick bracket, do the calculation, and then find it's over-designed. So you might bring that parameter in, make the brackets a little bit skinnier, and then run it again, find it's still over-designed, and keep on reducing the thickness until it fails, and then make it a bit thicker again. In this way, you can use the finite element analysis to optimize your designs. And not just for, lightweighting, but it's also for, cost effectiveness or for safety or stiffness or whatever might be valuable for your design. So there we've got the results. And let's have a quick look. Excellent, cool. All right, so what we can see here was the peak von Mises stress. Again, it's in the same area as we'd expect, and it's much the same. It's 236.9 megapascals, slightly more than aluminium because the steel actually weighs something and adds to the load of the structure. And if we click safety factor, again, we're going to see that, we're getting paid for this. So let's make sure that the safety factor is above 1.2. So it says loading, and we'll see peak minimum safety factor is 1.3. So great. Our insurance demanded 1.2, and we were able to deliver 1.3. Good. Now, what's the peak displacement? Have it load. And last time we freaked out because the aluminium deformed, 52.2 millimeters or whatever it might be. We might want to say, okay, it's got to be no more than 40. Oh, wonderful, good. Okay, so we can see here that the peak displacement of that end slat is 20 millimeters. Confidence inspiring, good. Excellent. All right, so we've got, so what we've done is we've loaded up our structure with linear static analysis. So we put on a load, we've hanged it on the end, and we verified the strength of those connections. However, the design department has thrown us a ball from left field. So they've put in an extra design stipulation that the structural resonance, the first natural frequency, the frequency at which this thing will resonate, cannot be less than 10 hertz. This might be for, vortex shedding, wind loading, or it might be for earthquake loading, whatever the reason might be. We have to make sure that this structure will not resonate below 10 hertz. So at the moment we have an apple in our throat. We don't know. How do we even do the calculations? Are we going to get the old textbooks out and do them? But luckily those calculations are very, very easy with Nastran. In fact, the setup is extremely minimal. So what we can do here is change the analysis type. So I could copy the analysis, do it all again, but let's go ahead and say edit. And we're going to change the analysis type from linear static to normal modes. And we're going to click OK. Lovely. Okay, so as you can see, it's brought over our material properties, it's brought over our load cases, our constraints. Wonderful. Now, in truth, the loads don't actually matter too much for the normal modes analysis, but it doesn't scrap them. Normal modes analysis mainly deals with the stiffness of the structure. So what we're going to do is set it to run, and what it's going to give us are the first 10 natural frequencies. So these are the first 10 frequencies, which if we put a loudspeaker next to them, it would start to shake and shake and shake and shake, and assuming no damping, it would eventually fatigue and break and fall apart. As you saw from Pete's earlier video with the Tacoma Narrow Bridge, they failed to account for the vortex shedding that was occurring over the bridge. And so what we were seeing was structural resonance, where the energy was building up with each wave of the thing. And as you saw, it was behaving like a wave. And the more you do these calculations, the more you appreciate that everything will behave like a guitar string under the right circumstances. But you don't want your design to fail for something so silly like that. So here we do our normal modes analysis. We'll click run. And there's very little input from our end. We're assuming no damping, so it's just going off, and it's going to give us the first 10 natural frequencies, a property of the structure. So while that calculates, I'll just show you some of the extra features of Nastran while we're at it. So in addition to making solid elements like we've done here, where we've broken up our components into lots of tetrahedrons, you can do all kinds of elements. So say, for example, beam elements. So say that you're working on a very, very large structure and you don't want to spend 20 hours calculating it. You can simplify elements to be beam structures. Or you might have, say, for example, thin-walled vessels, And rather than making very, very little elements that go all the way around and the elements number in the millions, what you might have are shell elements, which are greatly simplified elements. We also have things like connectors. So say, for example, you can put in like springs and pistons and rigid body connectors and whatnot. So to help us better describe the problem to the computer. All of these are tools that analysts generally tend to use to reduce the amount of computation that's required. Very, very valuable and extremely powerful, and all integrated directly into Inventor. And like I said earlier, the best part about all of this is that it lets you take an iterative design approach by minimizing the transitions between these changes and the actual calculations. You don't have to go to another software to say, for example, change the thickness of the beam. You can do it in Inventor and then remesh and rerun it in Nastran here. So fantastic. That calculation should be just about done. Here we go. Almost. There we go. Lovely. And what we're going to see here, don't freak out because the shape can be a little bit, is that we'll see the first 10 natural frequencies. So these are the ways in which the design will vibrate. And the vibration modes are all different from one another. However, the part that we really care about is this number. This is the first natural frequency, 16 Hertz. Beautiful. It's above our 10 Hertz specification. Okay, so I hope that was a good introduction to Nastran. I hope that it highlighted how you can not only prove how your design can function, but also that it meets specifications and that you can save money on prototyping. So rather than having built the original design out of mild steel and have it not pass the test, we actually did all the digital prototyping in the software and saved us a lot of time and a lot of money and gave our investors confidence that our design will work. So I'm going to hand you back to Pete, and thank you for your attention.
Thanks for that, Frankie. I think we can all agree that you can actually see the essence, really, of the power that really digital prototyping and FEA can actually have, really. And the great thing about that is you can have this now in-house to reduce your overall cost. Just before we kind of move on to the next session, in which my colleague Curtis is going to be talking about flexible manufacturing, and definitely something to stick around for and get interactive with, I wanted to really present another poll to you, because I'm really interested in your feedback, really, as you're hands-on in the market right now. And really to think about, okay, we've taken the idea of what the average cost associated with using a third party is within FEA and to perform the analysis work. But what I'm really interested in as well now is just having a little think about actually what percentages, really, of businesses here today, do you actually outsource your own FEA, and do you do your own testing or not as a business? So I'm just going to give you another kind of 20 seconds or so to choose through the answers. I'd be really keen to get that feedback and share that with the whole group. So I think we're just about there now with gathering that feedback. I really appreciate your input into this. I think it shows for some actually interesting numbers, really. So out of everybody here, we're actually looking at the fact that almost 40% of you actually do outsource your FEA work with third parties. And I really want you to reflect on that, I suppose, with what we all thought the average cost would be about that and what that really means to your business moving forward. And to be fair, it actually falls in line with where the overall manufacturing market sits within the UK, as nearly 62% of manufacturers within the UK also outsource their FEA. And I want to kind of stress something, I suppose, to you with this, because this really comes down to the main points of why you're here, why you want to discuss about how FEA can actually improve on your business. The amount of time savings you can get through testing in-house, through your own product designs, not only is it the fact of time spent with using third parties and waiting on delays with them, but also redesign, remanufacture, all those tests that have to happen, all those iterations that have to go for testing. Everything can be done in one place. You reduce your money and expenditure cost on your materials as well throughout the whole process. Not only that, if you have got a product which is going to need several iterations, send it using a third party once and get that back. Now imagine the power of that money being reinvested into your business. And I know straight away the first thing that a lot of people think is, oh my God, resource. How am I going to do this? These third parties exist for a reason. Well, the amazing thing is, the secret is, the majority of you already have access to this software. If you currently have a product design manufacturing collection today, you have access to Nastran, which is the tool that Frankie taught you through and showed you. So really, this is a great opportunity, not only to save money on the amount of external parts that you have to get involved, but reinvest that capital back into your business by upskilling your own team. They can gain real, tangible ways through the design process to actual manufacturing development of products to end up producing a product timely, cost effective, and get it out to the market. And it's generally going to be within a shorter space of time than what using a third party would be. So on that, I'd really want to thank you for your time this afternoon, and I want to thank Frankie as well. I think he's shared a wealth of knowledge with the FEA work, and I also think this brings us really nicely now into what Curtis is going to present with flexible manufacturing, which has got some real valuable insight, so definitely stay on for this one. Thanks again.